Hello, this is a short video trying to prove Euler's formula, e to the ix is equal to cosine x plus I sine x. For us to do this proof, we need a few things. We need some facts about the imaginary number I to the 0 is 1, just like anything to the 0 is 1. I to the first power is I to the second power is negative 1. That's actually the definition of the imaginary number. And then the square root of that, square root of negative 1 is equal to I. We have I to the third, that's I squared times I, so that's negative 1 times I, it's negative I. And then I to the fourth, we can look at that as I squared times I squared, so that's negative 1 times negative 1, that's positive 1. And then we can go I to the fifth, which is 1 times I, so that's like I to the first. We can go I to the sixth, that's like I to the fourth times I squared, so that's 1 times negative 1, so that's negative 1. And then you go on and you'll see that this forms a cycle of 4 different values. The 4 values are either 1, I, negative 1, or negative I. Okay, so that's really the only fact we need about imaginary numbers. The other stuff we'll take a look at information about series. So we're going to prove this particular formula using series. And for that, we need to know the series for e to the x, cosine x, and sine x, because those are the 3 functions that are involved. So the series for e to the x is x to the n over n factorial. And going from 0 to infinity, we got the 0 factorial is 1, n to the 0 is 1. 1 factorial is 1, and then we have 2 factorial, 3 factorial, etc. So this is a fairly easy series to remember, and we will make use of this in our class. The cosine is an even function, so we would expect even powers in your Taylor series expansion. And it's an alternating series, and it looks fairly straightforward as well. So we have x to the 0 over 0 factorial again, with positive 1. And then we have x squared over 2 factorial. This time it's negative. And then x to the 4th over 4 factorial positive. And then x to the 6th over 6 factorial with a negative. Okay, the sign is similar, except it's an odd function, so we will have odd powers for our polynomials, for our power functions in our polynomial. Okay, I think we're all set to prove this. So in order to prove this, what we're going to do is we're going to start with the exponential expansion and then replace the x values with, let's try that again. We're going to replace the x values with I times x. So remember, the expression that we're looking at was e to the ix. And so in our Taylor expansion, or our series, we're going to replace wherever we see an x, we're going to replace it with I times x. So let's go ahead and do that. There's a few of them here written out. Okay, after we do that, we will examine what's happening here, and we'll use the facts that we found about our the imaginary number, and let's see how that works out. So we have an I squared. Remember what I squared was? I squared was negative 1, so let's put a negative 1 out here, or just a negative sign. I cubed. If you remember what I cubed was negative I, so let's leave the I there, and then let's throw a negative sign out in front. I to the 4th. Remember, that's the one that turned into 1, so every multiple of 4 from now on will give you a value of 1. So let's get rid of that I. I to the fifth is I. I to the sixth is -1. Oh, I'm sorry, it's -I. Or that's -1. I to the seventh is going to be, this is the one that's going to be -I. And then I to the eighth, if we had that, will be +1. So I think let's just take it from here. So now that we have it simplified, let's see what else we can do. We can see that some of our terms have i's and some of our terms don't. So just let's see. What we could do maybe is we could just highlight or change the color of the terms that have i's in it, and then we'll do something with that. So if you're already seeing it, the terms with the I seem to be the terms with the odd powers, and then terms without the i's seem to be the term with the even powers. Let's make that clearer by moving our terms around. So this is our first term that has an I. Let's take that out. And then let's continue moving all the terms with the i's out of the way. And then let's just rely on the ... to say it's going to get generalized, and hopefully we'll see the generalization. So now that we have all the terms with the i's taken out, let's factor out the I. Let's take that I out. Whoops. Let's take that I out. Let's see, I, open parentheses, and close the parentheses on the other side. Oops, let's put a ... here before we close the parentheses. Alright, so let's take all the i's out, factor it all out, and it's an infinite series, but every single one of these terms has an I in it, so we can safely take that out. And then, as you can see, it looks very similar to our trig functions. Let's in fact make it look exactly like it. I think we did not have parentheses around the x's, so let's just, for the sake of making it look exactly the same, let's take away the parentheses. And then another thing we can do is for the negatives, we can just take those negative terms. Well, let me finish the x's first. Yeah, so these terms with a negative, let's just put the negative out in front so it'll be even clearer. We can do the same for the ones with the i's. And then here we go. If we take a look at this series and assume that it goes on forever, we can see that this series, well, let's put it in parentheses just to make it absolutely clear what's happening. This thing in the first set of parentheses looks like it's an even function, and if we take a look at our even function trig function over here, it's the cosine function. And then the term next to the I looks like it's an all odd powers alternating series, and that looks just like the sine function. So there we go. That basically completes our proof. Let's just throw in our last step here to say that this thing in the parentheses in the first term is going to be your cosine function, and then this term in the parentheses in the second term will be your sine function. Notice that there's an I in front of this the whole time, and so that I has to stay there. And then now our original e to the ix is equal to cosine x plus I sine x. And that is the end of our proof. So hope that'll be helpful, and good luck with the rest of your work.